Here we're simply going to apply Bernoulli's equation. And Bernoulli's equation simply compares two pressures at either ends. So we can say here P sub 1 plus the density times the acceleration due to gravity times the height at one end plus 1/2 times the density times V sub 1 squared will be equal to P sub 2 plus the density times G y sub 2 plus 1/2 rho V sub 2 squared. We know that due to the equation of continuity, we can say that then A sub 1, the cross-sectional area, sub 1 times V sub 1 is equaling A sub 2 times V sub 2. And we can then say that V sub 1 would be equal to V sub 2 multiplied by A sub 2 divided by A sub 1. And the cross-sectional area of the tank, however, A sub 1, is much larger than the cross-sectional area of the hull. So because A sub 1 is much greater than A sub 2, we can say that then V sub 1 is going to be much less than V sub 2. And so the 1/2 P sub V sub 1 squared term can be neglected. So essentially, we are going to eliminate this term because it is so small. And so now the Bernoulli's equation gives that 1/2 times rho V sub 2 squared is equaling the change in pressure P sub 2 minus P sub 1 plus the density times G sub y sub 1. And we can then use that P sub 2 is equaling the air pressure and then solve for the velocity sub 2. And so the velocity sub 2 would be equaling the square root of 2 times the change in pressure P sub 1 minus pressure of air divided by the density plus 2 times G times y sub 1. And we can solve. So this would be equaling, let's get a new line. V sub 2 would be equaling the square root of 2 times 3.039 times 10 to the 5th pascals divided by 1,030 kilograms per cubic meter. And this would be plus 2 times 9.8 meters per second squared multiplied by 11.0 meters. Extend the square root. And we have that V sub 2 is equaling 28.4 meters per second. This would be the speed through the hole. That is the end of the solution. Thank you for watching.